Good afternoon, everyone. First of all, I want to thank the organizers for giving me this opportunity to present my work. Today, I'm going to talk about active particles in the presence of soft obstacles. In particular, I want to study how they behave when there is soft obstacles. This is my group, and this work was done by my PhD student Ankit. He gave a talk yesterday. Well, of course, you guys are familiar with these active particles. Just from my side, let me show you a few videos. So these are like birds, fish, and the sheep, and these are artificial self-propelled particles, ionized particles. So these are the self-propelled particles, and now the question that we are asking is how these particles behave when they are diffusing in confined channels. If you take a flat channel like this, of length L, so here the degrees of freedom is same everywhere. I mean, along the transversal direction, since the width is same, the degrees of freedom is same. However, here in this, this sinusoidal shape channel, the degrees of freedom is not same everywhere. It's position dependent. For example, here particle has more space to explore, whereas here particle has less space to explore. That means the degrees of freedom is not same everywhere. It's position dependent. So that's how this entropy comes into the picture. And this entropy controls the diffusive behavior of the particles. That's what we are interested in. And not only that, we want to throw some soft obstacles in these channels and see how they behave, whether we can observe normal diffusion, subdiffusion, super diffusion, whatever. So the channels that we are interested in, there are this shape, sinusoidally, this of course is asymmetric channel. By the way, these are artificial channels. This we can make in the lab. There we can see these dimensions. So the same thing. The question that we are asking is like how they behave, how these active particles behave and diffuse in this soft, the presence of soft obstacles. So as a model system, we consider this symmetric shaped channel. Here, the particles are self-propelled. So this F0 is the self-propelled force, where this F is the force that is acting on along the length of the channel. So we need this force. Why? Because we want to observe the current as well. If there is no force, we may not observe any current, the velocity. Okay, that's the reason we switch on some external force, which is a constant force. And this is a perfectly periodic channel. Okay. So for this model system, we can write down this Langevin equation in the over-damped regime. So we can neglect inertia, and this is a damping force, and this is a force balance equation. Here the active force, this is the interaction between the soft obstacles and the channel. Here you can see this in this small video, where this blue particle, these are the active particles. This is how they interact with the soft obstacles. What do you mean by soft? Here these particles can penetrate, they can go inside this gray region. That's the meaning of the soft. So if they go deep inside, that means it's highly soft. If they just touch the surface and go back, that means they're hard. Doesn't mean, that's how we define soft and hard obstacles. And the second equation will take care of this rotational motion of the active particles, which is the property of the active particles. In the case of passive particles, we don't have to write down the second equation, that we know. And here we consider Gaussian white noise, no correlations, it's a delta correlated. And here at the channel boundary, we consider sliding boundary conditions. And it's a numerical study, we solve these equations, n number of particles. And just to get more information about the soft obstacles, for example, when particles are diffusing around, they can, in the presence of soft obstacles, they can squeeze through. Rather, they can push the boundaries and then just, rather they can just diffuse around. In the semi-soft obstacle, they can, the space is limited. That means it has to, push a bit hard to pass through these obstacles. Where in the case of hard obstacles, they can be trapped. These particles can be trapped by these hard obstacles. Sometimes these hard obstacles, they can form the small cavities, and these active particles can be trapped. So they can have zero diffusion at times. So just by changing the K value here, we can control the softness of the obstacles. Okay, this is the main control parameter in our model. And these are results. We calculate the mobility, non-linear mobility, which is nothing but the means velocity, or F. By the way, the small f is the scaling parameter. This basically is F, the constant force F upon kBt. I'll just take a minute to explain this F. The small f, in this model, the small f is f by kBt. That means we can couple the external force and the temperature. These can happen only in the case of this kind of particular channels. In the case, for example, if you consider one-dimensional channel, this f and t are independent. However, here in this case, this f and t can be coupled. We can define one single scaling parameter, that is small f. So this is how we define the nonlinear mobility, and this is mean square displacement. We can look at these two quantities as a function of the scaling parameter f. This is the behavior. So this dotted line, this is the case where we consider a flat channel filled with obstacles. Here, eta defines the density of the obstacles, and the k defines the strength of the softness, or you can say the k defines the softness of the obstacles. So in the case of, I mean, if you take a relatively soft obstacles in the for a flat channel, so the nonlinear mobility is slightly, it is like just less than 1, but it grows and finally it reaches 1 when f is very high. That means when you push the particle too hard, the mobility will be just 1 because mu is just equal to f, so the ratio will be 1. Okay. But if you consider a correlated channel, the sinusoidal channel, this mobility increases. There's a big drop here. The mobility increases monotonically. Only at higher force value it reaches the value 1. But in between, for intermediate value, for different softness of the obstacles, what you can see is there's a drop in this region. There's a drop in nonlinear mobility. That means mobility decays, right, sharply. Then, depending on the k value, sometimes it may increase, sometimes it may close to 0. That means if the obstacles are very hard, then nonlinear mobility is 0, as you can see from this picture. Soft, when k is relatively soft, then because of this high force, particles, that means particle can squeeze through squeeze through these soft obstacles. They can have a finite current. That's the reason there's a rise here in nonlinear mobility. And this is the corresponding effect to diffusion. It shows a Jain enhancement. I will show you why there is a Jain enhancement in the following slides. And we varied this translation diffusion as well as the rotation diffusion. And what we noticed was this dr doesn't play any role here. That means the rotational diffusion doesn't play any role. But however, this dt plays an important role. And in fact, that will give you a hint that what could be the critical k value with which we can define the soft and hard obstacles. For example, here there is a sudden drop in nonlinear mobility around 2.5 10 to the power 5. So this we can consider as like kind of a critical k. Okay, that will set you, that will give you, or rather that will tell you like what is soft, what is hard. Okay, and these are a few trajectories for different dt values, a smaller dt value and higher dt values. Almost done. So here we can see that particles just diffuse around and suddenly they just make higher, like these long jumps, and sometimes particles they're trapped depending on the value of dt and k, whatever. Right? So we can see various situations. That means particles squeeze through, they can have higher diffusion, sometimes they're trapped, sometimes they jump. Okay? So now we can look at the mean square displacement as a function of time. Okay? So in the longer time, t tends to infinity limit, what you can see is this mean square displacement, like t to the power alpha, where alpha equals to 1 in some cases, alpha equals to not equals to 1 in some cases, depending on the k value. That means we can observe normal diffusion, we can observe subdiffusion, we can have like super diffusion and so on. Okay, of course, depending on the force that you're applying along the length of the channel. So here alpha, the power alpha is a function of k. That's what we're plotting here. So for relatively small force, you can see that say that like particles are more or less, like they show this normal diffusion with some fluctuations, right? And for moderate force value, you can see the subdiffusion, and then there's a super diffusion for intermediate values of k. And the long for higher k value, that means in the case of hard obstacles, the particles are trapped. That means there's no diffusion at all. Okay, they're properly locked. And if you further increase force value, these fluctuations, they decrease. So it's more or less, like the behavior is more or less normal. That's because you're forcing the particle along the length of the direction, and for intermediate value of k, particles somehow squeeze through these obstacles and then pass, and then just try to go along the length of the channel. However, if you at a higher k value, as one would expect, particles will be trapped because these hard obstacles, they form the cavities. So that's the conclusions, and that's it. That's all I want to show you. Thank you.
So in this picture, the bottom right, so it seems, right. So it seems that there is a critical value of K which is independent of F, beyond which it becomes trapped. So what is that number? Where does this number come from? Is there any physical understanding for why that K beyond which, irrespective of F, it gets trapped?
So this, if you look at this picture, this one, for example, here. So if you, here what we're plotting is mu as a function of K, right? So mu is very high here, but suddenly the sudden drop in nonlinear mobility if you increase the K value. So that means what we're changing is the softness of the obstacles, right? So the thing is, I mean, analytically it's very difficult to find out this value, but at least from numerical simulations, we can get, I mean, we can take this around 2 into 10 to the power 5. Right. So that's at the limit. With just number, I mean, because this is a scale value, K is a scale value. The capital K is the actual K, and the small k is the scale value. It's capital K upon this KBT. That sets this scale, scale K value. It's just a number. I mean, I don't know, like why we get 2 and something, why not 1? I mean, that we don't know. But just from numerical simulations, we get that the value is around 2 points. Yes, just observation.
Any questions? If there are no questions, let's thank the speaker.